Hello.
Okay, so sorry?
Yeah, I just wanted to ask the question.
Okay, go ahead.
So I actually have a question on shells. So
Mhm.
in the lecture, it was mentioned that on the third shell or on the third energy level, there could be 8 electrons. Yeah, so on the first 2, second 8, and the third also 8. But isn't it 18?
It is 18, but first you start, let's say, feeling the 8 and then switch to the next level. So after 3p, we start feeling the 4s, not 3 further, okay?
Okay, yeah. Okay,
So
thank you.
let me share the screen for a second. Do you see my screen?
Mm-hmm.
Okay, so as you might remember from school, so we have 1s, 2s, 2p, 3s, 3p, 4s, and 3d. So the feeling of the orbitals starts from 1, then 2, then 2p, 3s, then 3p, 4s, and then it switches to 3d. So the maximum that s orbital can take is 2 electrons. So the maximum could be is s2, 1s2. Then we start with the second level. So it goes 2s2 and 2p6. Then we, after 2p6, we switch to the 3s. So it goes 3s2, 3p6. And after we fill these 3s2, 3p6, we start with 4s2, and then we go to 3d, okay?
Yes, okay, got that. Thank you.
That's why we have 2 maximum on the first level, 8 on the second, and 8 on the third.
Okay, thank you.
You're welcome. So the question from Fariza. I'm sharing the screen again. Okay, so the decay of neutron goes like this. So we obtain 1 protein, so it's neutron, 1 electron and neutrino, and also energy. So this single neutron becomes 1 proton, 1 electron, and neutrino, which means, for example, you have C14, and C has the atomic, so carbon has the atomic number 6, which means 6 protons are in the nucleus. And if we write them like this, so let's say neutrons will be like this, 4, 5, 6, 7, 8. And if you start counting, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this is the atomic mass, okay? If you subtract 6 protons from this mass, you will obtain 8 neutrons. Whenever we have one of these neutrons decayed, so let's say this guy, it decays. So it will decay into 1 proton, again, 1 electron, neutrino, and energy. So these 2 guys and energy will be escaping this place, but proton will stay in this place. So instead of this neutron, we will have another proton. And the proton plays a role of the identifier of the molecule, which means from carbon with the atomic number of 6, it becomes 1, 2, 3, 4, 5, 6, 7. It becomes nitrogen with the atomic number of 7. and this electron will have high energy. That's why it will be counted as the beta radiation.
Excuse me?
Yes.
Can I ask a question?
Mm-hmm.
In the presentation, there were a slide with type of bonds. There were anionic bonds, covalent bonds, and hydrogen.
Yes.
And there said that hydrogen bond is the weakest one.
Yes.
But however, when I had courses of chemistry, they said, and there we said that in the intermolecular forces, hydrogen bonding is the strongest. I am quite not understand. It's a different type.
I think you will need to have some readouts from other places. So just go back to there and try to read them again, because the weakest one is the hydrogen bond. But if you take the total amount of these hydrogen bonds inside, for example, solution or in the cell or cytoplasm, you will see that the number of formed hydrogen bonds is quite huge. So let's say that 1 mole of water has 6 times 10 to the power of 23 molecules, which means every molecule will be able to form this hydrogen bond. And if you sum all the energy that is accumulated within all hydrogen bonds of this region, you will understand that it's a huge, if you think about it, it's really huge amount of energy. Maybe that's what they mentioned during the other courses or during, for example, chemistry in school. But the thing is, if you take single bond, it will be the weakest. Is it clear?
Is it clear? Sorry. So the point is not in the single one, but in the amount of these bonds. Yes.
So if you take total, it will be a huge amount of energy. So you will need to kind of, sometimes you need to heat, for example, the sample to just make these hydrogen bonds get apart, okay? So the total energy is much higher than in chemical bonds of ions, for example.
Hello, excuse me, can I ask?
Yeah, just a second, Yerjan.
Okay.
Did I answer your question?
Yes, yes, yes. Thank you very much.
Okay, nice. Arjan, it's your turn.
Okay, thank you. So you said that if there is a neutron decay, there is a lot of energy will be released. Yes.
Yes.
Okay. So what is the difference between radioactive decay and nuclear fission?
There is no difference. It is the same.
It is the same thing, yes?
Yes, because you have, for example, nucleus, and the fission means this nucleus kind of is torn apart, okay? And this is the same as radioactive decay of the nucleus.
Okay. And could you please explain what does tracers mean?
Just a second, there was a question about tracers, I guess.
Good afternoon, Professor.
Yes.
May I ask a question?
I'm sure, wait a second, I'm not a professor, okay? I'm your teacher.
Okay. I have a question about bonds, like we have covalent, ionic, and hydrogen. And I didn't get the difference between covalent and ionic. I don't know, maybe it's about, maybe it's like depends on my background. Like I don't have any background in chemical bonds.
Okay.
And
I got the question.
Yep.
Just a second, Agbota, I will try to get references for the textbook but only from the next lecture. Okay, so about bonds, tracers, free radicals, and that's the three questions that we have for now. So we start with the free radicals and antioxidants. Okay, so what is the free radical? So let's say we had methane, and this methane was attacked by some energy that gave one of these hydrogens enough energy to split from the other side, from the other part of the molecule. So if you remember, methane looks like this. So let's say that this bond was attacked by energy, and it actually made this hydrogen split from the molecule. So now we have CH3 and one unpaired electron here. And whenever we have one unpaired electron with a high energy, because this energy was applied to it too, this molecule becomes very active. That's why it's called radical. And this molecule will try to find this unpaired electron to stabilize itself, okay? So let's say we don't have electron here, and the main goal of this molecule becomes to find this insufficient electron. So what it does, it actually attacks everything that is close to it. Usually it's a chain reaction, which means you have this molecule attacking other molecule, and the other molecule becomes the free radical. But let's say you have a cell. So in your cell you have the nucleus, and in nucleus you have DNA. So this DNA is a double-stranded molecule, and it has a lot of atoms in it on both sides. And these atoms are very good candidates for attacking of these free radicals. And whenever one of these radicals attacks it, so let's have one radical here coming. So it's free radical. It attacks the DNA and becomes a stable molecule. The thing about it, this part of DNA becomes very unstable. And what is the neighbor of this part? It's actually the other side of the double-stranded DNA. And this produces unrepaired binding. So if we have a gene here, so let's say this is the gene of hemoglobin, and whenever the RNA polymerase comes to this place to transcribe this region of the hemoglobin gene, it stops here because it cannot go further. This part is closed for the RNA polymerase. And this means that this cell stops growing, etc., etc. So usually we have the system inside our cells that tries to eliminate these double-stranded breaks or the damage of the DNA. And if we have the unrepaired DNA that is crucial for the cell, it starts the process of apoptosis. And apoptosis is a controlled death of the cell. So this cell decides to die, and it really dies. And this is the free radical induced apoptosis. Usually, to kind of fight these free radicals, the cells can produce so-called antioxidants. And these are usually something like fats or high carbon containing elements. So let's say we have a lot of carbons and they go to both sides, and usually these are fats, and they actually can donate one electron and still be a stable molecule. Sometimes whenever we have, let's say, the irradiation of the cell, let's say we had a nuclear bomb somewhere and we were looking at the patients, because of a lot of these free radicals that were attacking the cell, this cell cannot handle this situation itself with these fats or protectors or antioxidants. That's why we give people special drugs. We also feed them with the vegetables or fruits, or give them a lot of milk, etc., etc. So we try to kind of increase the level of antioxidants. So these antioxidants, they fight free radicals. And the better they fight, the healthier our organism is. Okay, I cannot access my chat. Oh, okay. So it is about the free radicals. Next question was about the tracers.
Sorry, but can elements itself be free radicals, or only compounds can be?
All molecules that you can imagine can become the free radicals if they have one unpaired electron that is in an active state. So if this electron is active, it becomes the free radical. And that's why it's actually very reactive, and it attacks everything that it senses.
So how about elements that are already exist in our organisms and they help us to function healthily? So what about them? Just why they are not free radicals? For example, like elements for a trace and for osmotic pressure body and bulk elements, etc.
So if they become the free radicals, and usually it's because of the excess of energy that comes from outer sources, whenever we have this situation, we have a very unstable state for our cells, and usually it means that we are diseased. We don't feel healthy. It becomes very dangerous and potentially lethal if the amount of free radicals is more than the organism can handle.
Okay.
Did I answer your question, or did I miss, like?
No, I got it.
Understood it with a mistake. Okay, miss. Next question was about the tracers. Okay, so let's say that we have metals. Actually, to understand it, we need to go a little back in the evolution. So I think I told about it in the lecture. So when we first had our Earth about 4 billion years ago, so it was covered with the primary ocean. And within this primary ocean, in this primary ocean, actually, so we had all these elements floating in a mix. There were not these sugar molecules or anything else. It was just a mixture of elements. So there were C and ferrum, cuprum, etc. And since we didn't have the proper atmosphere to protect us from UV, not us, but the Earth, this UV and also all these gamma, beta rays, they were bombarding all these molecules. And whenever we have molecule with high energy, it becomes very reactive, and it starts attacking or reacting with other molecules. And in this way, we spontaneously started having the increase of complexity. So from this mixture, we started receiving something like CH4. So this is the simplest organic molecule. And these organic molecules started kind of growing in numbers. And also because of this constant bombarding with UV and other energies, this process was going on and on and on. So the complexity was growing with time, the complexity of these molecules. So this is time, and this is complexity. And at some point, we started obtaining molecules that were very high in numbers, in atomic mass. So let's call them pre-enzymes or pre-catalyzers. And these molecules, they were needing the metals because, as you know from the chemistry course, almost all metals can be the catalyzers for other reactions. And let's say these pre-catalyzers, organic ones, they were also needing these metals like cuprum or other stuff. And from this moment, we started having a very complex molecules that were working together, I mean, with metals. And these metals, they saved their role in these processes because the next levels of evolution, they created a very ordered number of organic molecules and classes like sugars, proteins, fats. In the production of these guys, we still needed the same metals because the pre-catalyzers evolved in catalyzers or enzymes afterwards, which were still needing these metals, or any metal. And nowadays we have, just a second. Nowadays we have proteins called enzymes, and they have spatial conformation, like any shape you can imagine, they can have it. So let's say within the cell we have one enzyme that looks like this. And to activate this enzyme and make it work as it should work in the metabolism, catalyzing some part of the reaction, it really needs, for example, our iron. So whenever iron attached to this place, the enzyme becomes active and it's starting changing its conformation. So instead of this huge ball, it can become more suitable for some part of the reaction, but only if it's attached to iron. Okay, and from now, it can accept, the substrates 1 and substrate 2, and produce a product of the first enzyme. So the thing is, this place is very high, it has a very high affinity to ferrum, but it also can accept something else. Let's say something like lead or plumbum. And if instead of the ferrum, it has the lead, it will not change the conformation to this state. It will make it inaccessible for substrates. So instead of usual enzyme, we have something of a different shape. And this enzyme is kind of not functioning as we suppose it to function. That's why we have tracers. And these are efficient or beneficial elements. And we also have toxins. Toxins or poisons. That's why the plumbum is a poison and ferrum is the tracer. So they kind of work against each other, but only in the particular places and particular enzymes. Some of these elements, like plumbum or lead, they can also bind, for example, DNA. And in this case, whenever we have the binding of DNA with the lead, again, let's assume that there was an enzyme, RNA polymerase, that comes to this place, and it cannot pass it. So the cell stops producing the messenger RNAs. That's why some elements became poisons for us, like hydrargyrum, for example. So this is mercury. And it means that something that is not beneficial for us, is not potentially good for us, became poisons for us. Okay. So who is asking this question?
So may I ask the question about that? Can you hear me?
Yeah.
Okay, so can we consider the trace elements as catalysts of reactions in our organism? Because you have said that if ferrum is activated with active site, so it can become like suitable for substrate. So
Yes, so they are key players in these reactions.
So they are considered as catalysts?
Not always, because so as you know, something like platinum is the chemical catalyzer, but the catalyzing effect of it is very vague, so it doesn't do the specific job. It can do a lot of jobs at the same time. The jobs that kind of doesn't discriminate between the substrates. And if you take enzymes, they are highly specific, specialized. So one enzyme can only take these and these substrates, not anything else. But as the reminder from the past, we still have these tracers that activate them. So they are called activators and never catalyzer, okay? Because they themselves do not do the catalysis stuff. They just activate the real specified or specialized catalyzer called enzyme, okay?
Okay, thank you.
You're welcome. So I hope now you understand what are the...
It will be like coenzymes, yes?
Again, please, I can't hear you.
So metals like iron and others, platinum, will be coenzymes, yes? Like with...
Yes, you can call them coenzymes or enzyme activators. So some of them really play a role in the formation of this catalytic center,
Complex. Yes.
and some just play a role in the activation. It doesn't mean that ferrum or iron cannot be the coenzyme for some of the enzymes. It just means for this particular enzyme 1, it plays a role of activator, but in enzyme 2, it can play a role of the key element of the catalysis center. Okay.
Pause.
Again, please.
Hear me now?
Yes, now I
Excuse
hear.
me? Is it better?
Yes, yes.
Okay. Here is it about toxin poisons that stop enzyme from producing product. Also, there are some inhibitors that I know that stop enzyme from producing products too. So the main difference between them is that the effect of toxin poisons are irreversible, or
The thing is, it might be irreversible. It might be reversible. It depends on the enzyme and on the element. It also depends on the organism. So for some species, for example, iron can be a poison. But for mammals and for most of the eukaryotes, that could be our relatives. For example, we can assume that there are poisons, the same poisons for all of these species. So not all inhibitors are bad just because the inhibition is also controlled by enzymes, and most of the inhibitors are enzymes themselves. Okay, so there are, let's call, we have another small protein, which is an inhibitor of the enzyme 1. So let's say it has an affinity to this place, and whenever it gets here, everything on the metal part of this enzyme is being detached. So this is called the inhibition. It doesn't mean that we poisoned the enzyme. It just means that we made it inactive again. So actually inhibition is something in the contrast to activation. Is it clear?
yes, it is. Thank you.
You're welcome. Not always inhibitors are bad. They also play key roles, but for example, if you take toxins or the poisons, they are always bad. So whenever you apply them, you will have the diseased organism. So you will reduce the health. Okay, so the next question was about the bonds. Okay, so the covalent bond is something that could be explained like this. So let's say there is an element 1, and it has, let's say, 1 electron on its shell. And it starts pairing with the element 2 that can accept this electron, okay, and form a pair with this electron. So whenever we have these paired electrons, we speak of the covalent bond. And this is very strong. So to make them split, we need to apply a lot of energy. So next type is the ionic bond. And for example, just a second, we have sodium, and on its outer shell, we have one electron. And this guy is going to pair the chlorine, which has 7 electrons on the outer shell, and it pulls this electron here. Okay, so this electron comes from the sodium, and it starts kind of orbiting chlorine mostly. So this chlorine pulls the electron. And this bond, so this bond, when something pulls something else, it's called ionic. We don't have to apply a lot of energy, so let's call it moderate energy to split. And this energy might come from the hydrogen bonds, and I will tell you furthermore. So now I'm going to clean the screen, and next we switch to the hydrogen bonds. So let's say we have water. It doesn't have to be water. It might be anything that contains hydrogen. And if we take hydrogen, its electronegativity, or delta, is usually assumed to be with the plus sign, which means it doesn't hold the electron next to it. So almost all elements, they are stronger than hydrogen to kind of pull the electron. So usually hydrogen loses the electron inside the molecule, and this electron is pulled to the side of the more electronegative element. In this case, it's oxygen. So everything starts orbiting mostly the oxygen, and these parts become positively charged, while this part is negatively charged. So if you take this model and assume another part, let's say like this, in this molecule we have the same redistribution of the electrons, so everything goes to oxygen, and this part becomes negatively charged, and these two guys, plus and minus, they kind of get together, and that's what we called hydrogen bond. And the thing is, it's very weak. That's why we don't need a lot of energy to split. Okay, so why it's related to the ionic bonds? So if you remember, for example, sodium chloride, this part was looking almost like in this molecule. So chlorine would pull this electron from here and becomes negatively charged, while sodium becomes positive ion. And in this case, whenever we dissolve sodium chloride in the water, a lot of water molecules come to this place, with the negatively charged region, I mean to this sodium. And a lot of positively charged regions come to the chlorine. So let's go in like this. Show. And this energy becomes enough to split the ionic bond. So that's why we have this sodium chloride dissolved in water. And from now we have two ions. One is sodium with a positive charge, and one is chlorine with a negative charge. And this is the solution in water. And because water molecules are very potent in making hydrogen bonds, water is the universal solvent. In CAR, yes, you're right. So if the tracers or toxins change the structure, in one case, the substrate cannot bind to the active site, and in the case of tracers. And whenever we have toxins or poisons, the substrate cannot bind to it. So the reaction doesn't happen. The question from Amblayhan. So the enzymes are usually functioning inside the cell, and most of the time, immune system cannot enter the cell. So the thing is, the cells themselves, they have the system of protection that kind of tries to eliminate the unusual or dangerous compartments or proteins. So they usually mark it with a special sign. So this protein goes to the protease reaction, so protein decay reaction. And it is a very common process that usually happens because all of the enzymes, they have their expiration date. So let's say they can function only for 1 day, and after that, they cannot change the conformation so easily. So in this way, they will be sent to the proteolysis. But it's not the immune system.